Hi, and welcome back to Econometrics B. So this lecture is a follow-up on our lecture on multinomial responses. So today we're going to talk about how to actually implement the conditional logic model in Python. I'm going to show you basically analysis based on a simulated data. So we're going to simulate data from the random utility model, a model that's specified so that lives up to all the basically all the different assumptions underlying the conditional logic model. And then we're going to estimate the parameters right back. And then hopefully, the parameters we assume for the data generating process is going to be equal to those parameters that we estimate, or at least close. And then we later calculate a bunch of features of interest, such as, derivatives, elasticities, cross elasticities, and own elasticities. And then finally, I'm going to make a Monte Carlo experiment where we analyze the properties of the maximum likelihood estimator applied to the conditional logic model and see, does it look like that our parameters are, approximately normally distributed with a mean equal to the true value? What about t-statistics? Do they look standardly normally distributed? So in other words, are we close? Our approximation of using the asymptotic results, are they reasonable for this particular case? And how does that vary with the number of observations and stuff like that? That's the plan. Okay, so really just I'm going to make a short video on the conditional logic model. For that, we need a bunch of libraries, and basically most of the routines that you need is going to be buried down in this little library. It's called a Discrete Choice that you can just import. It's uploaded to GitHub to the repository on a multinomial logic model. So it should be available for you. And once you once you read it in, why don't we just quickly look at what is in that library? I'm just going to read it in, and then open my editor, and then you see here there's a bunch of routines that you have access to. The first one we're going to look at is the simulation module for simulating data that looks like this. Okay, I'm going to come back to it in just a second. So then that's really the next plan. We want to simulate and estimate a data set for conditional logic. So here's the example. We're going to have j equal to 5 alternatives. They're index 0 up to j minus 1. And then we need n equal to 10,000 observations. And we specify here a model that has 3 parameters. It's corresponding to 3 explanatory variables. That is 1, -1, and 2. So there's like one with a positive effect, one with negative effect, and one that with like a little bit bigger positive effect. That's kind of so we have a little bit of stuff to look at. And then basically I just call the sim data module that's buried down in discrete choice module, this function here that we have over here, ask for this particular type of data indexed by these 3 different parameters. And then it makes a little bit some assumptions about how the explanatory variables are distributed, but we can look at that right now. So really, so here that's a number of explanatory variables. That is the size of the parameter. Remember, for the conditional logic, we had 1 parameter for each of the explanatory variables, at least in the simplest case. And then we then generate some data that we call x, and some explanatory variables that are normally distributed. And then they have, these are standard normal, so I just add a number here to have it vary across the different alternatives what the mean is. So the first one has a mean of 3, and then the last one has a mean of 5, just to have a little bit of different effects. You may want to think about these different attributes as different things. Make your own interpretations, or go in and simulate others. If I really encourage you to play around with it. Now, once you got those explanatory variables, well, then we can go down and calculate the utility, which is essentially very simple. It's just x times beta. I don't know why we have this. We don't really need it, but that's doesn't matter. So this is x times beta, or utility or the deterministic component of the utility. Once we know x, we generate the ID extreme value distributed errors. So these are standard the extreme value errors, because we get this shape parameters the correlation parameter to 0. And then we have our combined utility of v and epsilon, and then we find out what is y, what is the argument that maximizes utility. So this is really an index between 0 and all the way up to j minus 1, depending on which alternative you take. So this is like just the random utility model. Okay, so having simulated some data, we can estimate the model, and there's a routine for doing so. I'm not going to go in details with it. You can go in and have a look at it yourself. It's essentially just doing maximal likelihood and presenting some of the results. So we go back over here, and then we're ready to rock. Okay, so this is what we get. It starts printing what is the initial likelihood before we do any optimization, and what is the gradient, not 0, but then fortunately the gradient is going to be 0 after we've optimized. So this is what we get. Do we get our estimates? Well, they're reasonably close. This is supposed to be 1, so 0.99, that's pretty good. And then this is supposed to be -1, this is supposed to be 1. So they're pretty close. And I would say if you look at the standard error that we estimated, they're also within the confidence intervals. Add and subtract roughly two times the standard error, then you got your 95 confidence interval, and surely this is the true value 1 is within those bounds. Okay, and that's what you would check if you want to see if your estimator is consistent for estimating the true parameter. Is your estimate within the standard error, or two times the standard error, or is the true value in that confidence interval? Well, then it looks like you kind of nailed it. And we did, so that's really good. Okay, we plotted the likelihood and so on. Now, what I want to show you here is that this number here, well, that depends on the data set, right? So if I simulate another data set, I'm going to get another number, okay? And now you see these numbers are changing every time I estimate the model. It's not because I'm doing anything with a method, it's because I'm simulating a new data set. And I didn't fix the seed, so for the random number generator, so this means a random number generator is just going to draw different data sets every time that you run this. So you can see they vary, these numbers, they go up and down, and basically that's kind of showing that the estimator that we get is a stochastic variable itself, because it depends on the data, right? So the questions, and we can analyze that later, is how is the distribution of that stochastic variable, and what is it? What does it mean? Is it true to the is it close to the is it close to the true value? Well, it certainly appears so. Sometimes it's above, sometimes below. What is the standard deviation? And is that standard deviation close to this number? That is our measure from theory for what the standard deviation of our estimator is. The standard error. Okay, and you see here, just from eyeballing the results, it's not totally out of the blue that it changes. 95% of the time, it's going to be within these two confidence intervals. But this is kind of eyeballing. We're going to do it much more clear in just a couple of minutes. Okay. So, but before we get there, let's just also calculate a couple of features of interest. And I talked about the marginal utility of money. Beta is a measure of marginal utility of money, but utility is kind of some theoretical measure that's not really observable. So we may want to actually rather compute the marginal effects with respect to a change in one of the explanatory variables, for example. And now these explanatory variables, they vary across alternatives. So let's suppose we call X, that's the price of alternative K. Well, what happens if I change the price of alternative K? So you got like 5 different alternatives, and say the 5th alternative, that's like a BMW, and alternative 0, that's like that's like a Fiat. So what is the effect of a change in the price of BMW on a Fiat, and so on and so forth, and also on the BMW itself? You can calculate things like that, and that's essentially just differentiating the choice probability or the market shares with respect to the attributes, which could be like the size of the the price, or maybe the things like the things you don't like it could be like how much does it pollute, or what is the cost, and so on. Okay, so Anyway, so we can calculate these effects here, and basically here what you see. Oh, let's go back. This is the expression you get for these partial effects. If you differentiate the logit formula, you're going to get this. Okay, and this, of course, this partial effects is only true for the logit model. It's going to be different for other discrete choice models, but the logit model gives this very simple partial effect. And what you will do is you just take the logit formula and then just differentiate with respect to xj or xik, and then you should get this. This is a nice exercise you can do yourself. Okay, but for now, we're just going to focus on how do we implement this formula, and I've just done that in Python, and that formula is really just implemented here. So you got the probability of alternative j times theta, and then 1 minus the probability j of alternative j if j is equal to k. Okay, so you got this indicator function right here, and that's also what we have over here. You got this indicator for being the attribute being the same as the probability or the alternative for the probability you're looking at. You got that right here, and then you got those probabilities with different probabilities here. So now you can immediately see that you know, if k is equal to j, so you're looking at like a derivative with respect to an attribute for the same alternative you're looking at the outcome for, then that effect is going to be positive if beta is positive, which is kind of very intuitive. You know, if you have a positive coefficient, say you know how nice is the car in some aspect, you know, so beta is positive. Well, then if you get more of that attribute, you get a higher market share of that particular alternative, right? So that particular car. And whereas all the other probability is going to fall. Okay, and we're going to actually see we can implement that and calculate the results. Okay, so here's some the matrix of derivatives, and see now you get a matrix of derivatives, right? Because the explanatory variables, they have, you know, we're changing the attributes here with respect to attributes of all the different alternatives. Okay, so it could be like so it could be like the size of, you know, car 1, 2, 3, 4, 5. That's what we're changing down here on the market shares for the different cars. Okay, so if you say increase, since I took the example size, it's like something we like because the first parameter is a positive one. You know, theta 0 is equal to 1. So basically, you know, you got the expected outcome here that you know, beta or theta is positive, so you got a positive derivative. That's what you get here. Whereas you get negative ones across all the other different alternatives. And see here, since market shares are going to be constant, right? So then when you make a marginal change in one place, because you know the probabilities are summing to 1, so you add all the market shares are going to be constant, right? So if you change one, you have to deduct from all the other ones. So a check here, and that's really a check for whether you coded this right, is that all these derivatives, they need to sum to 0. So if you increase the demand for this particular good, well, since the choices are mutually exclusive, it has to be taken from all the other alternatives. So these coefficients here summed together, they have to be equal to 0, and that's what I have done here for all the different attributes, all the different variables. So they do vary, and you see they're also different across the different alternatives. But we had the IDA problem, but that's only in terms of proportional substitution patterns. So that would not show up here. That will show up if we calculate elasticities, and that's what we're going to do right now. Okay. So, but the bottom line is, you know, you got a positive number off the diagonal, and you got negative numbers off and the off diagonal. We could look at the other coefficient, the one where the coefficient is negative. So we differentiate not with respect to the first variable, but with respect to the second one, and then you get the opposite pattern, right? So that, oh, you know, everything is all good. It's like we expected. Okay, and for the third one, so that's number 2. That's variable number. You know, with zero base indexing, then well, if you compare it to what we had before, then the average partial effects or all these derivatives are larger because beta is larger, and also because x is actually also larger. Okay. Anyway, so why don't we just put this back to the original and then move on and talk about elasticities? Because sometimes, you know, economists really like to calculate elasticity because then you kind of get these effects free of the unit. Okay, and one of the things that you can calculate there is just, you calculate the elasticity, and we already got the partial effect. We calculated that before, so I'm just multiplying with this ratio in front of it, and then what you see is that actually reduces. That reduces it, because that probability of the alternative you're analyzing is completely dropping out. And this means that there's no variation across the alternatives in the cross elasticities. They're going to only actually depend on the attribute you're changing, not the outcome variable that you're looking at. Okay, anyway, we can calculate these things, and they're also here embedded in the code. And see here, this formula here. Again, I'm just looping over all the different combinations, do a little plotting. This formula here is the one that corresponds to this formula right here. Okay, so that's pretty straightforward to implement. And then they have special cases, depending on whether k is equal to j. If it's like a own elasticity where k is equal to j, or it's a cross price elasticity. Here I'm assuming it's a price, right? It doesn't have to be a price, but a cross elasticity when k is different from j, and then you get this other effect. What you see here now is suddenly now the elasticities they depend on x, right? So now the sign is not determined solely with respect to beta, but that's because we are considering a percentage change. So if you're doing something like a percentage change in an attribute that is negative, well, that means that you get, you make it more negative, right? So that's some subtlety there. You have to keep your mind straight when you analyze these things, but these are generally interpretable. And what they really highlight is the as we talked about last time, the independence of irrelevant alternatives, as all these cross price elasticities are completely independent of the alternative. And that's what you can see here when you calculate a elasticity matrix with respect to a variable change in the first variable. Well, all these cross elasticities, they're equal to 0.17 for change in the attribute of the first alternative, okay, of the first variable, because we're looking at the first variable, okay, and so it's positive. It's still positive. It's opposite sign for the alternative where it contributes to the utility of that good, but then the substitution is coming proportionally from all the different alternatives because they have the same cross price elasticity. It's the same cross elasticity. All the off-diagonal elements here are the cross elasticities. Okay, and they're not only of opposite sign, they're of the exact same size. Okay, and that's what we talked about last time. The independence of irrelevant alternatives, the fact that the I extreme value terms are independent across alternatives means that essentially all these derivatives, or all these elasticities are going to be the same because of the proportional substitution patterns. Okay, and because the ratio of the probability of choosing two different alternatives does not depend on other alternatives that are not involved in that change. Okay, so that's the same pattern as you see here. Well, you can, this is like a big matrix, and you don't want to, if you report elasticities shows all these numbers that are completely identical, you want to do that for a model where they vary across the different alternatives, like the nested logit model, or say the random coefficient model. But we're not going to talk about that because we're not going to cover it. Okay, so but it really you can really clearly see what you're imposing in terms of restrictions on the substitution patterns. That's solely coming from the error term, the distribution that is correlated across uncorrelated across different alternatives. Anyway, so we can also report this number. Only focus on how to calculate the diagonal, present those results. That's done here. So these numbers here corresponds to the diagonal. Okay, so if you look at the first variable here, this is the own elasticity for choice alternative number one. When you look at the probability of choosing the first alternative 0 with respect to a change in all the attributes for that for different alternatives. And so this corresponds to the column or the diagonal that you got right here. Okay, so this is diagonal. Okay, these are the only different numbers that we have in terms of the own price elasticities. And then you can calculate also the basically the cross price elasticity. And then you see here for this first variable, well, that corresponds to all the cross price elasticities for the different variables. So you have like minus 0.17 here. That was 0.9 minus 0.17, then you got the 0.39. Well, that's the second one for the alternative 0, for alternative 1, and so on and so forth. And then you could do calculate them for different variables, and you see that the cross price elasticities, well, they have opposite sign for variable number 2 because theta 1 was negative and this the theta 0 was positive. And then also here you see they have opposite signs here, and then you see that the vast effect is bigger because you got like a higher coefficient. So things, seems intuitive and well understood. Okay, so I mean, what this number means is if I increase the attribute of alternative 0, then it's going to increase the demand for alternative 2 by 5.6%. Okay, and it's going to yeah, so that's really what is going on. Okay, anyway, so yeah, here's one where you can compare all of them. We can't see them anyway, but here I'm just listing all of them together, and yeah, we can look at it. Okay, so this is what you get, and so I've calculated all those different matrices for the different alternatives, and then you can compare. Okay. So anyway, we'll go back to the slideshow. I'm just going to skip that. Now I want to talk about Monte Carlo. Okay, so really we want to do a little analysis of some of the properties of the maximum likelihood estimator for the conditional logit model. And remember in the beginning we re-estimated the parameters, different samples, you got different results every time. We're going to look at that more systematically now. So what we're going to do here is we're going to do what we call a Monte Carlo experiment. Okay, so the idea is to first just specify kind of the parameters for the experimental design. So we have like a model with 2 parameters, theta 1 and theta 2. There, that has variables 1 and 2, and then k, that's a number of those experimental variables. And we have 1,000 observations, 10 alternatives, and we're going to do 500 different Monte Carlo samples. So what does that mean? So this part here is just the parameters of the model, and parameters and dimensions of the model, and this is the number of Monte Carlo samples. So here's the idea. What you do is, like I was actually doing Monte Carlo before. I was not systematic about collecting the results. So what we're going to do here, instead of me pressing the activating the notebook many different times, just looking at the number, we're going to do a loop. Okay, so we loop over all the just different Monte Carlo samples, and then for each time we're going to draw a new sample. Okay, so we have this data set that's simulated from the module that you have in the discrete choice discrete choice file, and you're going to get a new data set every single time. Okay, and then with those data sets, we can estimate a conditional logit. Okay, that gives you a new set of estimates every single time, just like you saw in the beginning. And I've suppressed the output. But actually, why don't we just like do 2 of them, and then say I want to see the output. So it's quiet false, and then you can see here it did actually estimate the model twice. Okay, and we got 2 different parameters. Okay, so why don't we do that more times? And we don't want to see this output. We just want to collect the results, and that's what we do right here. So we collect all the results from our conditional logit into this into this variable res. Okay, so that's pretty much what's going on. And then it says Monte Carlo done. That was fast, but we want to do more than 2. We want to do like say 500 estimation. It takes a little bit of time. You have to estimate the model and simulate the model 500 times, but not too much, because I coded up with the analytical derivatives, only 2 parameters, so it's kind of a feasible thing to do. Okay, it was done pretty quickly, so we can move on and then analyze these results. So what are we computing here? What I'm doing here is basically here I'm just putting 2 parameters taking two parameters and store them into some matrices. So here I have the theta hat parameter or parameter vector, and then I have the standard errors. I want to save those in matrices that I call MC theta and MC SE that are basically the number of Monte Carlo draws in the rows, and then the number of parameters in the columns, because we have like we have several parameters. We want to be able to look at all of them. And here you could just you can save anything. You could also calculate like what is the average partial effects, or what is some t statistic, or other things you can derive from the model, and then you can save those. Okay. And then what I want to plot out and say, okay, on average, in all these different tries, what was the let's just remove that. We don't need to take expectation. This is a true value from the data generating process, and we're not taking the mean of that. So that's what I'm plotting first. It's 1 and 2, and then we want to see here. What do we get on average across all these different samples? So I'm taking the mean with on the first axis, where you had all the different Monte Carlo draws, and then I'm going to get two numbers, right? One average for parameter 0, and then one for theta 1, okay, for the other one. And how do they look, right? They're pretty close to the true values. Actually, they're actually very close. Okay, so like 0.0 and 1.00, that's pretty close. So you do, and then actually, if you do this, I mean, in order to distinguish this whether this is bias due to the estimator or due to the Monte Carlo or just noise because of the Monte Carlo experiment, well, you would need to do some more draws. So we are doing 500. I think that's reasonable. Then we can also look at what about that bias between that variable and the true one. That's the expected bias that you get, and then you see, well, that's just one the true parameter minus that, and so the bias is relatively small here, and that is most likely due to small sample bias. But so you would need many draws to really get those last numbers away, or to discriminate between whether at that level of digits it's bias or it's Monte Carlo simulation. And then I calculate something called the Monte Carlo standard deviation, which is like basically just in that distribution of all those estimates, the standard deviation. You got many different estimates. Then you can calculate the standard deviations of all those estimates. Okay, I got 0.05 for the first parameter, 0.07 for the second parameter, and look at, if you take the mean of all the standard errors, they're very, very close. So our estimator of the standard errors are actually a pretty good estimator, because it measures how much is the variance going to be if I take independent samples and re-estimate the model again and again. So that's really, I think that's really or illuminating. And why don't we just also look at the entire distribution of those estimates? So we got two parameters, 1 and 2, and then you see you got different estimates, and so they have a distribution. And what we just did was like calculate what is the mean of that distribution, or what is the mean subtracted from the true value. Then that would be close to 0. And what is the standard deviation in that distribution? Well, that looks like actually 0.05. That's not really too bad, right? That would be 1.1. That's kind of the upper level of conditional of the confidence interval. It does look like we have 95% of the observations or the estimates within that range. You look at the other parameter, you can see there's a little bit larger variance, and you got a mean around 2, which is the true value. So these things add up with what we just saw on the previous slide, right? So we just have these standard deviations here, and here, these Monte Carlo standard deviations. Well, these are the standard deviations in these two different distributions of theta 0 and theta 1. Okay, so we can, but it doesn't have to be the parameters only that we're looking at. We can look at other things. We can look at like average partial effects, or whatever you're interested in, and see, does these average partial effects, do they, with the estimator we're looking at, add up with what we will expect to see, say, at the true parameters. Okay. Or you can calculate, say, a distribution of a t-statistic, and then that's what I'm doing here. So I'm calculating basically what is the theta minus theta minus the true value divided by the standard error. What is that a t-statistic for? Well, that's a t-statistic for basically and basically that our estimator is equal to the true value, okay, and then we divide by the standard error, okay. Now under the null, that this is actually true, we know this is going to be standard normally distributed, right? At least as n go to infinity. In finite sample, it's going to be like t distributed or something, but probably not for no, just forget about that. But just we rely on asymptotic results, let n go to infinity, then this is going to be standard normally distributed. And so the question is, does it actually look like it's standard normally distributed? So are our t statistics valid to test whether that distribution is true, is right? And it suddenly appears so. If you look at this, well, we probably need a little bit more, more Monte Carlo estimates in order to really nail down what is the distribution here. But it does look like, here you got your plus minus 2, you got some, eyeballing says to me, you got 95% of these intervals in here, and you got most in the middle. This, I mean, we could probably try to run some more and see if we get something that's a little bit more smooth. So I'm gonna say, like, let's do 2,000 Monte Carlo draws instead, and then see if the distribution looks nicer. It's going to take a little bit of time, but I'm talking and talking and talking, so eventually we're going to be there. So is it done? Well, it's not done yet. We can look at the estimates, but I think it's kind of clear that that distribution here, well, it's a little bit jittery, but maybe it's not too far from the normal distribution. And then the question is, I mean, it looks like our approximation, asymptotic approximation, looks reasonable. Okay, if you of course you would need to test with this, in fact, normally distributed, but it's not like it's totally all over the place from like minus 10 to minus 5, right? The standard error is actually providing a pretty good estimate whether for those 95% of the estimates are within that range. Okay. I think maybe it's done in the oven, and it says done, Monte Carlo done. So I can update my results here and see, get a new distribution. Looks more normally distributed now, as it should. And this also looks a little bit nicer. Start to look like a normal distribution. And so now you see, of course, if you want to, get enough information about Monte Carlo distribution, well, you need to take a lot of draws in order to really see that distribution. Anyway, so that's what I had to say about this. But of course, there's much more you can do. I mean, we didn't analyze all the asymptotic properties of this maximum likelihood estimator for logit. It's relevant to ask other parameters. What happens as n go to infinity? Do we really, can we verify that the estimator is root n consistent for theta? So does it appear that if you calculate, say, the root n times theta minus theta naught, and do that for many different values of theta, and calculate, say, the mean and the standard errors of that, does it look like it's approaching a standard distribution with the variance covariance matrix that you would estimate? So would that have the standard error that you have estimated as a standard deviation? Well, you need to multiply, of course, with n, but then and what happens? Another way to say it is: does it appear that this statistic here, as you increase n, that the standard deviation of it is approaching to a constant? That's what we are assuming. Maximum likelihood and M estimators generally have a limiting distribution with a constant variance if you multiply them with the difference to the true value with root n. And then you can also try not to multiply with root n, and you would see that distribution collapse. Okay. And basically whether it's root n or some other root, or what determines the rate of convergence, well, that depends on what you multiply in front of them. You could try different roots of n, like the cubic root, and that would be like a slower convergence, and then that number that makes that distribution constant, that standard deviation constant, that's going to be the rate of your convergence. So can you, by looking at different estimators, see if by varying n, plotting the standard deviation, can you see if it's approaching that is constant? So you can show that you get like root and consistency of your estimate. There's so many questions you can analyze in this, like, this test bed for analyzing estimators. Like, what would happen if J increases? Well, intuitively, we don't get more parameters. Potentially, we actually get more variation. Maybe actually we get more precise results. That would not be the case for the multinomial logit, right? Because as you increase the number of alternatives, you also increase the number of parameters. So you can analyze the properties basically by changing different things. What about the distribution of other statistics, like elasticities, like derivatives, like the log odds ratio? All the things you can calculate from this model, are they consistent? Are they asymptotic normal? Are they so are the assumptions that we're making in order to make inference around them correct? Okay. What about if the logit is misspecified? Okay, so what can you afford? So in terms of various misspecifications for your model generally, I mean, we were assuming, for example, that you have these ID extreme values errors. What they have another distribution? What about if there are potential correlation across alternatives? Well, maybe you're going to get bias in those. In those elasticities, okay? They're not going to be constant across the different alternatives, okay? What about the neglected heterogeneity? Well, that depends on what type of heterogeneity you neglect and so on, okay? What about if I estimate the logit with another estimator? Could I somehow, estimate those elasticities? Say if I have a linear model, could I estimate like one particular elasticity of interest? Would that add up with the true elasticity from this model? So, because logit model practically more difficult than bilinear model. So you can do so many things in this test bed to really try to understand what are the properties of this estimator that you're working with, and that's all I have to say. So have fun, play with the code, and actually you're gonna use these principles for your assignment next week, where we're going to focus on another model, or the binary response model for panel data, but the principles are exactly the same. Okay, so bye bye. Have a good weekend, and see you soon.